Namaskar. Welcome to Prakash on Basics. I am Prakash Zog. Last time we saw how uranium is mined and refined, and what we get out of it is known as yellow cake or UOC, uranium ore concentrate. As I told you, roughly around 80% of it is the desired material present in it. So, this is the first step. Most of this yellow cake is U3O8. The technical name for it is triuranium octooxide. Yellow cake is good enough for us. But this yellow cake has, as I told you last time also, 99.3% of uranium 238 and 0.7% of uranium 235. There is a small trace of uranium 234 also. That's negligible. And what the whole world needs today is uranium 235. That's our basic source of nuclear energy. So, we need to get more of uranium 235 than the available uranium 238. The process of increasing the percentage of uranium 235 in whatever available uranium is present is known as enrichment. It is a highly scientific and technologically advanced process. Uh, it's a bit complicated, but very interesting. And as intelligent human beings, we must, and present day situations, talking of uranium is something that we must all know about. Uh, Somehow we need to either separate out these isotopes or increase the percentage available of one of them, which is uranium 235. And that's pretty difficult because their properties are practically the same, and the physical properties aren't very far away from each other. The reason is there is hardly any difference in their masses. If you just look at the numbers, 238 divided by 235 will give you about 1.0127. So that boils, if you convert to percentage, it turns out to be about 1.27%. So there is hardly any difference in their mass. So the technology used has to be very sophisticated. Uh, it's so complicated that even today there are only about five or six uh, officially known factories worldwide that do that enrichment job. Actually, the enrichment program started at Manhattan during the Manhattan Project itself. That is where the atomic bombs were first made. And that was around 1937, 38, somewhere when they started working on these processes. The whole thing involves a number of steps: purification, conversion into uranium hexafluoride, then the enrichment process, and then the formation of fuel cells, and so forth. It's a very long process and lot of scientific concepts. So I'll break it down into much smaller bits, shorter ones, so that it becomes simple for non-science people who are interested in knowing more details. So let's begin. The first part that I'm going to talk of today is how this uranium uh, oxide or yellow cake is purified, then how it is converted to uranium hexafluoride, and how the first major type of refinement process, which is gas diffusion process, works. So let's begin. Uh, First of all, that yellow cake, which is packed in those 200 pound drums is brought to another factory. This yellow cake or USC is purified. This is done by solvent extraction. Uh, so what it is done is it is dissolved in a chemical where it will dissolve only the uranium salts, and then what is obtained is ammonium diuranate. This is filtered out, dried, and calcinated. I told you what calcination is: heating at high temperatures to bake it, probably. And that's around 850, 860 degrees that it is carried out. And what it does is it converts all this into uranium trioxide. That means uranium and three oxygen atoms. Now, one more step is carried out, that one oxygen is removed by a reducing agent, which could be either hydrogen or nitrogen, and it becomes uranium dioxide. So, this becomes the starting material. It is then treated or heated with hydrogen fluoride, HF. This is an extremely corrosive acid, but what is used invariably is in its vapor form. And because of this heating process, it converts this uranium dioxide into uranium tetrafluoride. Tetra is 4. So you have one uranium atom and 4 fluorine atoms are added on. But that's not enough. So what you do is you take this uranium tetrafluoride and heat it with fluorine gas itself. And because of this, two more fluorine atoms get added on, and the whole system becomes UF6. Uranium 6 is hexa, so uranium hexafluoride. And for all processes, this is the starting point. This UF6 is a pure solid, and it can sublimate. That means if you heat it, it will like camphor. It will directly convert into its gas form. So this solid is uh, packed in special cylinders for further processing as in how it is required. There's one question that would obviously arise. Fluorine is not very common. It's a cost. It's not. It's comparatively it's less in nature. So why go in for fluorine? Um, there are two or three major reasons for this. First, all these processes require a gaseous form of the substance. Now, if you take uranium, you have to vaporize it, and the boiling point of uranium is 4131 degrees Celsius, too high. While the boiling point of uranium hexafluoride is only 50 degrees Celsius. And so industry wise, becomes a extremely manageable temperature. So convert it into vapor, it's not very, it's just a little hot, that's all. And then you can continue the process. So it becomes much more manageable. Secondly, uh, fluorine doesn't have any other isotopes that are commonly known. So normally they don't. So what happens is in all these uranium hexafluoride that you have got, fluorine is always the same. Only uranium is either 238 or 235. So the properties that you have to control and separate out do not involve chlorine at all. It is only the uranium that we have to bother about. And so naturally, the process is going to become that much simpler. But then, for those who remember from chemistry, these are all halogen compounds. Fluorine followed by chlorine, and chlorine is quite common on our Earth. Uh, so why not use chlorine rather than fluorine? One, it has two isotopes that are very commonly known, but they also tried using uranium tetrachloride as raw material, and then carried out the process and tried to go ahead. But the trouble is, it was found that the byproduct was phosgene, a gas, COCl2, and that's extremely poisonous, extremely reactive, extremely corrosive, that will damage all the equipment that is around. So chlorine was dropped out and fluorine was tried. Actually, in the Manhattan Project, uh, before other processes could be tried out, a technique using cyclotron, a particle accelerator in circular manner, was tried. But the trouble was the whole system was extremely complicated and it produced only 2 micrograms of uranium 235 per hour. 1 gram, break it down into million parts, and that's a microgram. So the amount of generated uranium 235 was extremely low. So this technique had to be given up. And what was tried was the gas diffusion process. And that's the process that really triggered on the method of obtaining enriched uranium. This process, there is a scientific base, obviously. It is based on what is known as the kinetic theory of gases. And it has a number of laws. One of the laws in this is known as Graham's law of diffusion. I'll just tell you what the law is. It says that the rate of diffusion is inversely proportional to the square root of the molecular weight of the gas. Let's keep it to the side. What it means is that there is a process called diffusion in which gases tend to merge into each other. Even if there is a boundary, they will go across the boundary and merge into each other. This happens spontaneously. It's like two gases that keep next to each other and they'll start, some of them will go this side, some will go this side, and so forth. This phenomenon is known as diffusion. What it says is that the rate of diffusion is higher if the gas is lighter. If the gas is lighter, its kinetic energy mass is lower, so naturally its velocity will be more. If its velocity is more, it will penetrate across better. And that's what the law says. So the rate of diffusion will be greater for lighter gases. Let's take a simpler example. Suppose I have a big wire mesh and there are a lot of, mm, let's say, flies and bees on both sides. But one side the pressure is a little more. So naturally, the one where pressure is more, they'll try to go across to the other side. But since the flies are smaller, they'll get across the mesh faster. And since they also tend to fly faster, they'll get across faster. And so gradually the concentration of flies on one side will start reducing and the concentration of flies on the other side will start increasing. This is exactly what is done in this gas diffusion process. So what does it have? It has a uh, cylinder, vertical usually, and inside it there is a porous layer, and inside that is a pipe that gives you uranium hexafluoride gas at high pressure. So once it enters in, the same pipe will then cause the chamber to fill up at high pressure and an outlet is taken from there itself. Outside the porous region, the pressure will be lower and then there is an outlet pipe from there also. So naturally, through the porous material, uranium hexafluoride will begin to diffuse. But since uranium 235 atoms are lighter, their kinetic energy being the same, their velocities will be more, and so they will diffuse to a greater extent. So gradually the concentration of uranium 235 hexafluoride on the other side will start becoming more than the one inside. So naturally the inner stream of gas has less uranium 235. It is known as the depleted stream, and the outer stream of gas will become enriched stream of gas, and they are both taken out by their own pipes. The central depleted one is either given back to the same system or processed in a different manner, while the enriched one pipe that comes out is given to the input of the next chamber. So there the enrichment process goes one step further, and again the output is given to the third one and the fourth one and the fifth one. This technique of arranging systems in one after the other is technically known as cascade formation. So a very large number of such chambers are connected in cascade, and these cascades will result into gradual increase in the percentage of uranium 35, uranium 235 in that particular part of the gas. In the Manhattan project, when the process, this one process was started off, they had 3,000 such cascaded cylinders. And remember, long back I talked of resistances in series and parallel. Same way, they have been connected either in series, and to increase the output, you connect a number of them in parallel in this manner and increase the process. So the cylinders are connected, the chambers are connected in series and parallel, and a large amount of gas then goes through the process. But you need 3,000 of them. The reason is very simple. This is a very slow and a time consuming process. Every time the percentage increase will depend upon how many of these lucky ones have diffused to the other side, gradually increasing the percentage. You can't even talk in terms of 1%. So it's a very low percentage in every cycle. And so gradually the percentage begins to increase. And this is how enriched uranium hexafluoride is obtained. That depleted stream is either processed separately or fed back into the whole system again, so that again uranium 235 will keep on getting extracted. The percentage of uranium 235 obtained increased in this manner is measured, and naturally this enriched UF6 gas is graded according to it, where, low percentage or high percentage or very high percentage and so forth. I'll come to that a little later. So this is the first type of enrichment process that started off. It was very slow. It was extremely time consuming. And so better technique was immediately tried and rather first discovered and then tried out. That is known as gas centrifugation. And there is a newer and a far better method nowadays available, which involves laser techniques. Those two we will talk of next time. Till you digest this one first. Uh, if you have liked whatever I have said, like and subscribe to this channel. Pass on this information to your friends. See if you can see some diagrams and look up information about gas diffusion process that is used for uranium refinement. Um, and we'll talk of the better techniques next time. Till we meet again. Namaskar.